I'm aiming to walk you through different topics since that we have quite a bit of time, focusing on the scientific discovery team, and finally I'm going to move to the idea generation part. So, when we think about large language models or AI agents, we generally think them as tools. So tools to which we say what we want. For example, we wanted to create a website, implement a website, or do a market research, and they go and do it, right? So that's the common understanding of large language models. But I would like you to also see an extension of that. So in my opinion, large language models or AI agents, they are not only useful as tools which perform what we want, but also they are very useful in bringing up ideas. So for example, bringing ideas, helping us to brainstorm about scientific discoveries, how to improve a certain methodology in any discipline. It could be a social science, it could be another thing. And we have been observing some applications of this emerging in past years. So for example, two very notable work from recent years was AlphaTensor and AlphaCode from DeepMind. So AlphaTensor, for example, is a method they have developed to discover better matrix multiplication algorithms, more efficient matrix multiplication algorithms or implementations than what has been invented by humans over past decades. And AlphaCode similarly invents faster sorting algorithms than previously known methods. So they were able to come up with novel and more efficient or faster sorting algorithms. So when we start thinking of agents or agentic workflows, this is actually becoming even much more interesting. So Google just recently released their AI co-scientist. So AI co-scientist is a publication where they use AI agents to make scientific discoveries in biomedical domain. So I won't go into specifics on what they have discovered. And there was also another work previously, I think by the end of last year, which was Sakana AI scientist. Sakana AI is by the way, a Japanese startup founded by the inventor of transformers. And Sakana's AI scientist is a bit different. It automates the research process from end to end. So they don't just discover a methodology, but they also at the end get a publication with full experiments, etc. And recently they had another work, which was, by the way, Sakana's AI scientist. They just had a publication accepted to an ICLR workshop just recently. And they have another work, which is AI CUDA engineer. And AI CUDA engineer, given a deep learning architecture, it invents or it automates finding or implementing efficient CUDA kernels for that deep learning architecture or activation function, whatever. So it's able to make basically deep learning models perform more efficiently by implementing the CUDA kernels autonomously. So if we look at AI co-scientists a bit closer, basically it starts by a scientist which is interacting with the system. So it's basically a collaboration work, and the scientist provides a research goal. He or she is also able to add an idea, review an idea, and based on that, the co-scientist makes a research plan. It does literature exploration. It does simulated scientific debate, for example, to brainstorm a methodology, and also basically it have some sort of kernel mechanism which selects the best idea to proceed with, and it probably takes inspiration from other ideas or simplify ideas or combine different ideas which are emerge out of this debates or brainstorming, agentic brainstorming process. And then there's also a review or critic system or process as well. And Sakana's AI scientist is also similar, basically, but here I think that the main difference is here the core idea actually comes from the LLM. So LLM provides an idea or plan an innovation. Then it checks the scholar, like Google Scholar or Semantic Scholar, to see if that idea is novel. Then it scores and archives those ideas, and for each idea it creates an experimentation template, and then it implements the experiment and executes it. And finally, basically, probably if the experiment fails or if the scores are not satisfactory, probably it updates maybe the plan, experiment plan, or does some debugging, and finally it produces plots, visualizations, and writes the publication and reviews the publication to also provide feedback for the initial idea or planning phase. So by doing this, basically they automate the end-to-end publication, research publication process. And as I said, they were successful in getting one paper accepted to an ICLR workshop. So I must say, I actually like have implemented previously some AI agents for like different functions here, such as, for example, like when I wrote the Evolver paper, like the results of experiments, the experimental section is fully written by an AI agent. Actually, the presentation of the paper has been prepared by an AI agent. Also, the literature section is done by another AI agent. So I've been actually already like benefiting from agents or agentic workflows a lot in my research, including like helping me, like for example, brainstorming ideas. So for example, I provide a methodology that I implement, and I ask like how this can be improved, or like what else can I add to the methodology implemented in this work. Or I get help in, for example, some coding tasks. So I come up with a new idea, and then I use LLM to maybe quickly implement a part of that idea, and so on. So although I haven't created such a workflow for the research publication case, I have been like using pieces to accelerate my work. So, but in Explain, we have been also doing quite similar things. So we have in patents we take, or in different research streams we have, I have a similar mindset in how I approach to large language models or agents. So Evolver is a clear example of that. So as you know, Evolver is one of our patented technologies, which has been recently deployed also to our agentification framework. And it is capable to observe an agentic system and its output, and then brainstorm modifications on that system, and implement those modifications, and then make evaluations, and at the end document like what changes resulted in, like what kind of changes in the output. So it's basically quite relevant to the work I have like mentioned here, and I'm like Evolver, basically the patent and the work was earlier than like many of the work here, but I certainly get like inspiration from the research environment, like the focus on this area in the research community. And last year, I also took a couple of other patents. So you are familiar with Evolver, but maybe you are not as familiar with these other patents. So one of them, which I want to like discuss at the end of the talk, which I think is as important as Evolver, is the following: an autonomous meta framework for enterprise multi-agent AI use case idea generation and implementation. So actually, all of these patents, or right now we have POC, some production level deployments, they have been emerged from different problems we have been observing while I was working on AI solutions, basically to help our customers. So Evolver, basically, it emerged from a need that I observed that optimizing a system, prompts of a system or workflow takes much more time than the initial implementation of a system. And the idea generation patent also emerged from a need. So often, for example, let's say we have a company from a certain industry. So let's say Saudi Telecom or Minister of Finance, and they can be really from diverse industry. And we are experts in AI, so we know what we can do there, which are like technically feasible, but we don't really know those industries, right? So, and often sales were asking us to do some research, come up with some use cases, and like basically I needed a way. I thought that it would be nice to have a way to auto-generate those ideas. So let's say in our agent framework there are a set of tools, and we have a target industry. We can ask LLM to come up with different ideas of agentic AI solutions. And I will show like some results later on, and it's able to actually come up with very similar ideas, which we have presented to customers, so for which we have some internal solutions like media monitoring or RFP response generator. Like it's not necessarily us who needs to come up with these ideas, but we can leverage from AI agents or large language models in brainstorming and maybe doing a basic implementation and even creating some example outputs. So that's why I think this is very important. And most recently, we have been also developing some examples with our agentic framework, like cookbook examples. And what I heard from the presentations, people generally said like the hardest part was coming up with the viable idea. And also there has been some like criticisms on, like why we have implemented these ideas, but not these ideas, which has been relevant to our customers, because we could maybe like present those. So basically, this system, when it is fully alive, it can resolve that problem. It can not just generate ideas in mass, but also it can prioritize different ideas. So the system I already have a POC for. It's basically criticize or reviews each idea as an investor, almost like an investor, to judge the market size of that idea, to judge the competitor landscape. And although I implemented that as a workflow, it could be also extended to do external research, for example, like reading industry trends, or doing competitive analysis, understanding what some competitive landscape in the industry is doing with AI. And then when we go to customers, we can go and say, like, these are what your competitors is doing, and we think that we have an idea, we have a couple of ideas for like better like use cases to help you. In fact, I also implemented a system which generates like does the research and does some kind of like product market fit analysis. So for example, let's say we will talk with the Ministry of Defense. So it basically reads the reports online. It also understands, for example, like what Saudi Ministry of Defense is maybe like talking online about potential uses of AI or their existing use cases. And based on that, it makes a sales meeting preparation where it lists different ideas and also explain like how I explain can help them to realize those ideas, and also backing like those ideas or use cases with the research done in terms of the industry. So that's one thing. So another patent we have provisioned is about automatically like code testing the system. So another problem we faced was we want to demonstrate some proof of concepts to customers, but we want to create them or create some example outputs even before we have access to their data or their tools. And that requires some simulation of tools, the human interactions. And if we would be able to simulate those, we can also simulate some faults. So what happens when a tool is broken or there's a human mistake, for example, in using the AI agent we have or interacting with the AI agent we have. And the final one was another solution we have developed about so it's a business intelligence system, but the difference from Incorta or the other BI system is that you don't tell it what kind of insights like you want it to extract, but it brainstorms what would be different valuable insights given data of an enterprise, and then it extracts them, and then from the insights generated, it compiles reports for different departments on how they can improve their operations. So here it's also important to understand that when you have ability to, for example, extract thousands of different business insights from a data automatically or generate thousands of ideas, not all of them require to be perfect. So when you automatically extract that amount, you can also eliminate some. Okay, so I want to also quickly talk about the ICLR publications. We have a couple of ICLR publications we have, which has been also relevant to this thought or this domain. So basically, they have started with a question. So AI is making discoveries in matrix multiplications or biomedical domain, but can it also do discoveries in quantitative finance, and how we can do that? So I did 3 applications for this. So one was basically the discovery of risk-adjusted metrics. So the risk-adjusted metrics like Sharpe, Kalmar, Omega, Sortino ratios, they are used in finance in order to evaluate the health of a trading strategy or a stock, for example, based on its prices. The second one was discovery of portfolio allocation methods. So this is a hot research area, the portfolio optimization or portfolio allocation. And the methods which has been developed here, they are actually like not perfect, I would say, when you evaluate their performance in out-of-sample scenarios or out-of-distribution scenarios. Like most of the, like basically the state-of-art portfolio allocation methods developed so far by humans, like over at least half a century, they are actually underperforming, holding a equally-weighted uniform portfolios. So like we may say they are not very ideal, or they are not where they should be. And the third publication was about automated feature engineering. So in quantitative finance, basically we develop predictive models, like to predict the future price per stock. And often, like so far, basically people were doing that by a repository or library of features, which has been developed by quants. But like what if we use LLMs to auto-generate more advanced, more sophisticated features that could maximize our predictive capability? So this is relevant to AutoML. So the AutoML frameworks like Flam, or at upper side you see like a typical scientific discovery process of a human, like how we come up with state-of-art methods, or how we come up with novel methods. So basically we have a knowledge of the literature. We read, for example, literature surveys or recent papers, and then we identify maybe some like state-of-art methodologies we want to improve upon, and we come up with different ideas. We have some hypotheses, and then we basically make modifications on an existing methodology, and then we do evaluation. And if things works, great. We have a novel method which is the state of art. And otherwise, we go back and then we basically work on another thing or come up with different alternative ideas. And large language models are great for it, because basically for each of those functions, they have different capabilities. So they have the cross-domain knowledge, like implicit knowledge from the training of the large language model. And like one step beyond it, they are also able to go and search basically publications as well. And they have language and code understanding capabilities, so they can go and check some like GitHub implementations, maybe decide, like for example, identify some security flaws or improvement areas in certain implementations, some ideas to make it maybe computationally more efficient. And they have critical thinking and reasoning capability, and they are able to automate the implementation. And for the evaluation part, they are capable of making tool usage, and they are also able to interpret the experimental results. And they are also, of course, useful for reporting due to their language generation capabilities. And basically, this makes them a great evolutionary operator as well. So basically, like there has been previous evolutionary methods like grammatical evolution, but we can now replace different evolutionary operators implemented with LLM. And why we can do that? Because basically, for example, we can provide large language model 2 different ideas or methodologies or implementations and ask it to come up with more implementations or methods, which are like by providing few shot examples. We can ask it to do crossovers. We can ask it to combine different implementations or ideas. We can ask it to look at a code and generate basically ideas for how to make improvements, like develop hypotheses. And we can ask it to make those hypothesized modifications. So here it doesn't just act like a mutation operator, but it's actually a directed mutation operator, which is great because in many evolutionary algorithm or strategies, we, for example, make mutations randomly as part of the search process, but here we can do more intelligent mutations emerging from ideas. And they're also able to do scoring and interpretation, as I mentioned. They can also score, for example, not just quantitative results, but also they can make some like qualitative evaluations, analyze visualizations, for example, or let's say, so recently I implemented a system which generates web page layout, and then it says the screenshot of the web page automatically, and it calls a visual LLM. And the visual LLM gives a textual feedback on how the layout is and whether it can be like how it can be improved. So it criticizes the layout given visually. So here, when we say evaluation possible, we can also think about further opportunities, and it can also act as a selection operator. So it can basically, let's say we create multiple methods. So LLM can help us to like select most viable of these methods as parents for further evolutionary process. Okay, so I talked about Sharpe ratio. So here, basically, what I aimed was to invent a new Sharpe ratio, which correlates better with the future investment performance of an asset more than the Sharpe ratio itself. So that was my objective. So as I said today, Sharpe ratio is very commonly used for evaluating trading strategies, investments. But I will show you some experimental results. Actually, it has only like 0.13 ranking correlation with future performance, which is a very weak correlation. But the method I developed here was able to invent a better metric, which has 3 times correlations, like over 0.4 with the future performances of assets. And this was thanks to basically the evolutionary process I have mentioned or described, which is a form of quality diversity optimization, which is also called illumination. So illumination, basically, the difference from the typical optimization system, illumination tries to illuminate all of the optimization landscape. It doesn't just want to find a single global minima, or which would be likely to stack in a local minima, but it tries to reveal all of the multiple of the global minimas or local minimas. So it travels through the search space. And for that, I instructed the LLM to generate metrics in PyTorch. I will also show you my prompts. And I applied cross-asset and cross-time validation to ensure the robustness of the metrics to evaluate their out-of-sample capability. And the method, in most basic sense, it basically evaluates the generalization capability of the invented metrics or algorithms, and then it ranks the metrics by quality and diversity to select parents for crossover. And after the crossover, it mutates different variants and evaluates them again. So maybe it mutates like 20 variants, like new variants at once. And there is also another LLM prompt to generate hypotheses before the modification, so some ideation stage, which enables directed mutations, which are more likely to lead improvements or helps us to search viable solutions quicker. So these are the prompts. I may share the presentation later, but basically like giving some few shot examples, it is instructed to act as a financial expert or and generate more metrics. So the first one actually is the crossover prompt. Given the examples, it combines the strengths of those examples to come up with a new metric, and then it generates hypotheses to how to improve that metric, and finally it applies hypothesis through the mutation task. And there are some constraints like use efficient matrix operations rather than for loops, etc. So try to come up with like novel but meaningful changes inspired from literature, etc. So this is an example of thinking process of the large language model. First, it basically analyzes the current algorithm, which has been produced from the crossover, and it basically explains that. So the algorithm that checks this, combines this, like use entropy, etc., and then it produces a final metric. And then it basically finds different avenues or pathways on like what kind of improvements could be done, such as like using wavelets, like exploiting or leveraging regime adaptation, using like latent risk factors to derive new features or kernel overfitting, using like time decaying rates because the recent data adapts more heavily to the market changes. It's like improving the noise handling or robustness, etc. So what can be done further in the most recent methodology to improve? So in Evolver, this was actually also similar. Evolver also tells us, like you can add this agent, this task, and this can lead to an improvement in the output. Okay, so as I said, I have been able to find metrics which are like much more powerful than Sharpe ratio, which is used by like almost all of the industry, which is great. So why this is useful? So it's actually interesting that people rely on something which has only 0.13 correlation with the actual feature values to do their analysis on their investments or to select assets. So obtaining something over 0.4 correlation makes you like much more confident in, for example, selecting or pre-filtering stocks or assets in your methods. Or you can also use that metric as a portfolio optimization target in order to optimize your portfolio, and you can also leverage it to evaluate your strategy backtest. So I also tried the metric in. So what if I use that metric and select, let's say, 20% or 25% of the stocks from a large asset universe and invest into those stocks? And what has been observed, basically, it doubles the investment performance of the industry adapted metrics. So which also shows how that ranking correlation translates to the investment performance. Okay, and then basically I was over with that, so I quickly also tried if it can generate not just metrics but also the portfolio optimization or allocation heuristics directly, and it has been also successful in that. The methodology was identical, so just the prompts have been changed slightly and the experiment part, and it has been able to basically outperform the uniform portfolio, the equal-weighted portfolio, by more than 100%. And as I said, the equal-weighted portfolio is actually a very difficult benchmark to outperform. There are many publications about that, like showing that what is thought of state-of-art methods are actually inferior from a uniform portfolio. And you may have heard the SP 500 generally outperforms maybe like 90% of professional investors. So that's partly the reason. And finally, I decided to also apply it to generate features like the ones on the right. So those features, along with like hundreds of other features, were generated automatically by LLMs. So like considering that we have an AutoML system in place, as you know, like gradient boosted trees, they have the feature selection capability, right? So theoretically, the more you add features, the more the performance should get better without overfitting if the hypertuning is done right. So basically obtaining a large bag of robust features, especially if they have consistent predictive capability or for for individual assets out of a large asset universe or for during different times, is very important because it enables you to distribute your bets into uncorrelated predictors, right? So you don't rely on a single or a small set of features to place your bets, but if you have a large uncorrelated set of bets, basically the robustness of the outcome improves, because even if some of those bets fails in out of distribution situation, you trust that the majority of those indicators or bets are still viable. So here the methodology was simply as follows. So given a few shot examples of features which has been generated before, generate more features, then use Flam Framer to hypertune a predictive model for feature performance prediction with time series cross-validation, and then rank those features by quality and diversity, for which I actually even use Sharpe values to select which few shot examples you want to use for the next iteration. And so this part also makes it quality diversity optimization or illumination. And the features are implemented again in PyTorch. So here, basically, this plot shows the feature importance. The height of the bar shows the feature importance, and the color of the bar shows in which iteration they have been discovered. And we see that we have like plenty of dark blue features on the left side, which means that the system keeps on discovering more and more important features. So it is capable of continuing discovering more important features as it iterates, which is very important. And also, like this plot also shows that over iterations, by the way, like in each iteration, 10 features have been discovered. So we see a reducing trend, like decreasing trend in the validation mean absolute error, as well as the test mean absolute error. And if you use those predictions from that like regression model for ranking assets, we see that the correlation of our predictor for the feature performance also increases over time, over iterations. Also, we see that the normalized discounted cumulative gain, which shows basically here when we rank all of the stocks, how successful we are at the top of the ranking and the bottom of the ranking. So how good we are able to identify a set of most successful stocks and like devastating stocks that you need to avoid. So we also see that it reaches to quite like high correlations as you add more features.